In this video, I'm going to work a more complicated calorimetry problem. So here we've got not just mixing two things at different temperatures, but you'll notice that one of them is something that could undergo a phase transition. And the details of these problems are going to vary with the numbers. So we can imagine a situation where instead of having 50 grams of ice at -20, what if we had 5,000 grams of ice at -20? And just a little bit of water. We can imagine that that ice is going to cool that water down, and the ice is still going to be below zero, and so there's going to be continual heat transfer from the ice to the water, and that water is going to start freezing. And maybe all of that water will freeze, and then we'll end up with the ice and what was the water reaching equilibrium at some temperature below zero. Or we can imagine a problem where we had not 50 grams of ice, but half a gram of ice and 500 grams of hot water. And in that case, we know that all the ice would melt and that we'd reach an equilibrium temperature a little bit below the 80 degrees C. So the problem, what makes these questions challenging is that we actually have to figure out what kind of problem it is before we even start. Does all the ice melt? Or does the water freeze? And so we have to do some sort of preliminary work before we try to get to that final question, which is what is the final temperature? So I'll model that entire process here. So we know there's going to be some heat transfer from the water to the ice because they're at different temperatures. And so there's really the possibilities, right? Depending upon the relative amounts of the ice and the water, we could melt all the ice or we could freeze all the water, or they can meet at 0 degrees C and we may melt some of the ice. So we have to really figure out which of those three possibilities is right before we try to calculate a number for T final. So let's do that part first. So let's ask the questions, how much are each of the heats for the possible process that could happen? So for instance, so we have to ask how much heat would be released if the hot water cooled all the way down to zero. We don't know yet that it will, but we want to figure out that number first. So how much heat would be released if the hot water cooled all the way down to 0 degrees C? We've got to set up a different symbol for each quantity. A common mistake for students to make is to have delta T as a variable, and there'll be more than one thing that changes temperature. So you want to make sure you put subscripts on that to note which thing you're talking about. So here we're talking about delta T for the hot water. Over here we're talking about the heat capacity of liquid water, and here we're talking about the mass of that hot water that we started with. So let's write those numbers in. So we had 60 grams of water. We have the heat capacity of liquid water is 4.184 joules per gram per degree C. And delta T for the hot water, if we went all the way to zero, is T final of 0 degrees minus T initial of 80 degrees. So the heat that would be released if the water were to do all this, if the water were to cool down, is going to end up being 20.1 kilojoules. So that's if the water cooled down, that's how much heat would be released from the water. So from the water's point of view, it would be a negative number. Okay, so that's one piece in the puzzle. Let's figure out how much heat now would be gained by the ice if it were to warm up all the way to 0 degrees C. Okay, so now we're going to ask what would happen if the ice were to go all the way up to 0 degrees C. How much heat would it have to gain to do that? So we don't know that the ice is going to do this, but we need to figure this number out, because later we're going to use these numbers to figure out what class of problem we have. If it's a class of problem where all the ice melts, or all the water cools down all the way to zero, etc. So let's go ahead and do this. Now, what we don't want to do is write the equation like this, right? We want to specify which quantities we're talking about. So we're talking about the mass of the ice and the heat capacity of ice. We have to use the proper heat capacity. It's in solid form, so the heat capacity is different from liquid water. And we're talking about the delta T specifically for the ice. Okay, and now we can write in the numbers. So we've got 50 grams of ice, and we have a heat capacity of ice. If we look at our equation sheet, we can see that it is 2.1 joules per gram per degree C. And our delta T here is a T final of 0 degrees C minus our initial, and our initial is a negative 20. So we can see our delta T is going to end up being a positive 20 degrees C. And if we plug those numbers in, we get that this is going to be 2.1 kilojoules. Okay, so if the ice were to get all the way to 0, there's a chance that it will melt. And so we have to see how much heat would be gained if all the ice were to actually melt. Because keep in mind, at this point, at this item 2, we've warmed the ice up, but it's still solid. It's just ice at 0 degrees C. So we haven't actually melted it yet. So that'll be the next step. So now we're going to ask, we have that ice that we already took in the previous step up to 0. What if it were to all melt? If it did, how much heat would be absorbed? So for that, we write our heat equation, MC delta T. We think, wait a second, temperature of ice doesn't change when it's melting. Obviously, this is wrong. We've got a phase transition. So it's going to be the moles of ice times the heat of fusion. And we don't directly have the moles of ice, but we realize we're given the mass of ice. So if we take the mass of ice and divide it by the molar mass of water, that's going to give us our moles of ice. So let's plug those numbers in. So we've got 50 grams of ice, and we've got a molar mass of 18 grams per mole. So we can see that's going to cancel and gives us units of moles. We multiply by the heat of fusion of ice, 6.01 kilojoules per mole, 16.7 kilojoules. Okay, so let's go ahead and show our unit conversion or unit cancellation here. So we're canceling that. We've got moles. So moles on the bottom of the bottom is going to give us moles on top. And so those moles will cancel with these moles, so we end up with kilojoules. Okay, so we have our answer in kilojoules, and this is if all the ice that's already at 0 goes ahead and melts. We're going to have to put that much heat in to melt it. Okay, so now we're ready to compare these problems, and that'll tell us what kind of problem we have. Okay, so I've just copied down what we've done on the previous few slides here, and that's that if we want all the ice to melt, we've got to supply, if we want all the ice to warm up to 0 degrees C, we need to supply 2.1 kilojoules. If all the ice melts, we're going to need 16.7 kilojoules on top of this. So first we heat the ice up and then we melt it. And on the other hand, if the hot water cools all the way down to 0, it's going to release 20.1 kilojoules. Well, notice something. We've got the hot water is giving heat off. It's going to be absorbed over here. But notice that we don't need all this heat to do this, to heat the ice up and melt it. So what's going to happen is we're going to be taking heat from the hot water and putting it into the ice, and we're going to heat it up and we're going to melt it, but there's still heat left over. So that tells us that we're not going to actually take this hot water and take it all the way down to 0. So this number is not the physically realistic one we're going to need, but these are. Okay, so these are. We are indeed going to melt all the ice, and then that melt water is going to warm up and meet the hot water at some intermediate temperature between 0 and the initial temperature of the hot water. So by doing this preliminary work, we know what's going on inside that insulated cup, and now we're ready to actually work the problem.